Screening tests play an important role in public health. While they don't diagnose a disease, they are useful for telling us how likely someone is to have it and whether or not they should have follow-up testing. In this video, I'm going to take you through a web application that allows you to explore the findings from a study looking at the effectiveness of a screening test and calculate some important quantities for determining how good the test is. Let's get oriented to the structure of this table. On the columns, we have the disease presence or absence as determined by a gold standard, like the definitive way of determining the diagnosis, a blood test or a culture, something along those lines. The rows represent the results of the screening test, whether they were positive or negative. Looking at the column totals then, we see that 50 out of 1,000 subjects had the disease and the other 950 didn't. Similarly, if we look at the row totals, we see that 140 had a positive test result and 860 didn't. If we look at the cells within the table, we have up in the right corner a little acronym TP, FN, FP, TN. Those represent true positives. For example, the 45 subjects that had the disease and tested positive for the disease, those are true positives. Over 5 subjects that were disease positive but tested negative, so those were false negatives. They yielded a false test result or a negative test result, but they actually had the disease. Similarly, if we look at the cells for the disease absent column, we have false positives of 95. Those are subjects that didn't have the disease but gave a positive test result. And we had 855 subjects that didn't have the disease and gave a negative test result. So we have false positives and true negatives. And from these numbers, we can start to assess how well the screening test aligns with the gold standard diagnosis. Let's customize this table to reflect the results of a screening test study that was comparing amniocentesis, which involves drawing a small amount of amniotic fluid from the uterus to determine whether or not the fetus is affected by a genetic disorder, to a screening test that is less invasive and see how that screening test performs relative to the gold standard. I'll change disease present to reflect the results of the amniocentesis study with affected fetus and unaffected fetus. And I'll leave my screening test as positive and negative. Now, there were 9 affected fetuses that tested positive and 1 that didn't. And there were 351 unaffected fetuses that yielded a false positive test, and 4,049 that yielded a negative test. You can see how the row totals and the overall total were updated as I entered and customized the cell counts. A good screening test will turn up positive a high percentage of the time among subjects that truly have the disease, and it will turn up negative a large percentage of the time among subjects that don't have the disease. These measures are known as the sensitivity and specificity. Below the table are tiles that contain calculations for these quantities. Hovering over the sensitivity tile highlights the table elements that are used in that calculation. Not only does it calculate the 90% sensitivity, but it gives me the formula in terms of the true positives and false negatives that are used in that calculation, and then the calculation as it pertains to our specific numbers in the table. The sensitivity of the test is the probability of a positive test result among those that have the disease. This can be computed from the table, focusing on the column pertaining to the gold standard of those that truly have the disease. Similarly, the specificity, hovering over that tile, highlights the section of the table that is used in calculating that quantity. This is the probability of a negative test among those that don't have the disease. So it involves the column of the subjects in the study determined by the gold standard not to have the disease. And the specificity is computed using this formula with the true negatives over all of the subjects that didn't have the disease. This similarly shows the quantities from the table used in that calculation. If the sensitivity is the probability of a positive test given subjects have the disease, one question that comes up is what's the probability a subject has the disease given they obtained a positive test result? That's different than the specificity. This is known as the positive predictive value. The positive and negative predictive values can be computed from the table similarly by focusing on the test positive row for the positive predictive value. This takes the true positives over all of the positive tests. So the formula indicates the true positives are in the numerator and all the positive tests, whether they were true or false positives, in the denominator. So that is 9 over 360. The negative predictive value similarly calculates the true negatives over all of those that tested negative from the screening test. This quantity of 2.5% indicates that when a positive test is observed, there is only a 2.5% chance that the fetus is affected by the genetic disorder. So that means there will probably be a lot of false positive tests from a screening test like this. The negative predictive value, however, is very high, meaning whenever a negative test is obtained, there is almost no chance that the fetus actually has the genetic disorder. Additional information about the likelihood of negative and positive tests given the disease status can be obtained from the likelihood ratio. Hovering over the information icon shows you how to interpret that likelihood ratio. This is an expression of how likely a positive test is among people with the disease relative to those without it. So someone with the disease is 12.3 times more likely to get a positive test than someone without the genetic disorder. Similarly, the negative likelihood ratio test tells us how likely someone is to get a negative test result if they have the disease relative to someone without it. Under that are some clinical interpretations of all of those quantities that help solidify what those measures mean. An important consideration in the positive and negative predictive values is the prevalence of the disease or the condition under investigation. The prevalence of that condition can have a strong impact on the positive and negative predictive values. For instance, if the disease is very rare, even if the sensitivity and specificity of the screening test are really high, the positive predictive value can still be very low. To illustrate this, you can toggle this disease prevalence button, and let's indicate that a disease affects 1% of the population, and we have a very sensitive and a very specific test at 95% each. Notice that the resulting positive predictive value for that rare condition is still pretty low, only 16%. That means the probability of having the disease if someone obtains a positive test result is still only 16%. There is a greater chance that they don't have the disease even in the presence of a positive test result. However, what we thought about the subject before the test was that there was a 1% chance they had the disease. That has now gone up to a 16% chance that they have the disease. So that is an important consideration in what to do moving forward as far as follow-up testing in subjects with positive test results. In addition to the simulator that shows the positive and negative predictive values for different combinations of disease prevalence, sensitivity, and specificity, there are key concepts that can be highlighted here in terms of the sensitivity versus the positive predictive value, the differing interpretations of those two quantities, and The same thing for specificity and negative predictive value and how these things might be applied in the